All right, everyone. This is the video lecture companion to the Chapter 18 notes. This is the first week of our online class, and so this is the first video lecture. This video is meant to be watched with the notes. I recommend having this video open in one window and the slideshow open in a separate window, and so you can step through them both together. I'll let you know which page of the slideshow that I am on, and stop, rewind as you need to. So on Mondays, just go ahead and get in the habit. On Mondays, your assignment is to watch the videos, read through the notes, start your homework, and have questions ready for the study sessions that I hold Tuesday through Friday. I will be here available, ready for study sessions, having a Google Meet ready for anyone to drop into or out of, from 10 a.m. to noon every Tuesday through Friday. I recommend you try to be present for about 2 to 3 hours worth of study session, because then if you factor in the hour for this video, then that's the amount of lecture time that you would normally get. Lost my train of thought. It even happens when I'm recording. So the reason there's so much study session time is not because you have to be there for all of it. It's just to give everyone options for when they're available. I tried to keep it to when we would normally meet anyway, but I figure everyone's schedule's pretty crazy right now, so I extended it to noon, and I made it every day Tuesday through Friday, so you can come when you're available. Come prepared with questions, listen in to other people's questions, we'll work through examples together, we'll talk through every concept that you need. I will also be filming those and posting those too. So, you will have a wealth of backlog material to be able to watch, to answer any questions you have, email me anytime. And you'll also have your lab assignments and homework and quizzes to work on over the week. For right now, let's get into Chapter 18. So if you open up the slideshow, on slide 1 is just the title slide. Slide 2, this is Chapter 18, and Chapter 18 is about RC circuits. R stands for resistor, C stands for capacitor. We've studied each of them separately. We're going to begin today with just a little more resistors only, and then we are going to combine the two together. And a circuit that has both resistors and capacitors in it is called an RC circuit. So that's where the name comes from. If you go down to slide number 3, this has some review questions. I do recommend giving these a quick look. These are questions just related to some topics from previous weeks. And so please look over these on your own if you are rusty. One of them is about resistivity and drift velocity. The next one is about resistivity changing as it relates to temperature. Slide number 4, we're now getting into RC circuits, and we're beginning with the battery, the voltage source, what actually causes the circuit to work. You need a battery or something acting as a voltage source in order for electric current to flow. That is because the voltage is the pressure that drives the current to move through the circuit. So the battery, if it's a battery circuit, the battery is the voltage supply. It has a different amount of potential on each side, and the current exits the battery. And just as a refresher, the symbol for a battery is the two plates of different sizes with a plus and a minus. So that is the symbol for a battery. And there's a different certain voltage drop across it, and that is the voltage drop across the entire circuit. Now, if you move on to slide number 5, batteries are subject to principles known as Kirchhoff's laws. And there are 2 Kirchhoff's laws that we are going to examine. I've written the formal definition, but also sort of the more straightforward definition as it relates to this class. Kirchhoff's current law states, the actual textbook wordy definition is, the algebraic sum of currents in a network of conductors meeting at a point is 0. What I want you to actually take away from that is the total current that exits the battery has to also enter back into the other side of that battery. When you create a circuit, a whole circuit, doesn't matter what kind of circuit it is, what elements you have in it, what its orientation of elements added into it, how, the size of it, etc. Any electrical current that exits this battery, so I've got some amount of current I coming out, that amount of current has to go through the entire circuit and then come back. So, current, if we just put a number on it for the sake of simplicity, let's say it's a 6 amp circuit. If 6 amps exits the battery, 6 amps has to come back to the battery. Now, in a series circuit, what that means is you have a couple resistors in series. There's only one path to follow through in a series circuit. So, this 6 amps of current is going to travel through every single element and then come back to the battery. So every single element in the circuit is going to get 6 amps worth of current. So in a series circuit, the one amount of current just flows around the whole circuit and then comes back to the battery. It's a little different in a parallel circuit, but Kirchhoff's law does still hold true. So in a parallel circuit, let's say we have 3 branches. And for the sake of simplicity, I'm just going to say that these are all the same size resistor, same resistance. 6 amps exits the battery. 6 amps flows to this particular junction. And then it's going to start splitting down these paths. And this is like a junction in a river. When water flows down a river and it hits a split in the river, some water can go this way, some water can go this way, some water can go this way. The same water molecule cannot go down all 3 forks at once. So the amount of current does have to split here. Since all these resistors are all the same size, I know that the 6 amps is going to get evenly divided back down the 3 paths. So each path will get 2 amps of that 6. So the current did split, but in order to have a complete circuit, it's all going to meet back up right here. After these junctions come back together, all 3 of these 2 amp pathways meet back up and reconvene to become 6 amps again. So, in any circuit, the current that exits the battery has to come back into it. If 6 amps enters this region of the circuit, it may split within that junction and within that chunk, but by the time it exits that chunk, it has to come back up to be 6 amps again. So that's Kirchhoff's current law. I'm going to change things a little bit now as we start talking about Kirchhoff's voltage law. Kirchhoff's voltage law. So, like the current law applied to the current in a circuit, the voltage law applies to the voltage in a circuit, specifically the voltage drop across the circuit as a whole and also each circuit element as a whole. And so Kirchhoff's voltage law states, kind of like the current law, that the voltage drop across the battery has to be the voltage drop of the entire circuit. So, if we say that this is a 6-volt battery, that means we have a zone of 6 volts of potential on the positive side and a zone of 0 volts of potential on the minus side. There has to be a difference of 6 across the 2 leads of the battery. Now, that 6 volts of potential exists everywhere on this side of the circuit before they get pushed through a resistor. And so every resistor in a parallel circuit gets the same amount of resistance. In this particular circuit, all these resistors are going to get the same voltage drop across them because we're going from this combined large zone on this half of the circuit of 6 volts over to this half of the circuit, which is in the big 0 volt zone. So every single resistor in this circuit has a 6 volt drop. So in every single pathway, the potential drops from 6 to 0. We are now at 0 volts of potential here coming back into the battery. So Kirchhoff's voltage law holds true. The voltage drop across the battery is the voltage drop across the whole circuit, because we dropped 6 volts through each of these pathways. That means from here to here we dropped 6, here to here we dropped 6, here to here we dropped 6, and from here to here across the entire circuit we dropped 6 volts. The law, Kirchhoff's voltage law, does hold true for series circuits. It's just a tiny bit different. So I'm just going to redraw this as a series circuit real quick. For simplicity's sake, we're just going to keep all the resistors as being the same size as each other. Now, in this specific case, the pathway doesn't split. So the current, if we were looking at the current has to go through every single element. And that does not happen all at once. There's no longer one big zone of 6 and one big zone of 0. Instead, we have a 6 volt zone here, another zone here after we've crossed this resistor, another zone here after we've crossed this resistor, and then after crossing this resistor, we're in the 0 volt zone. So every zone there after a resistor has its own total potential amount as it relates to the potential of the entire circuit. Now, because all these resistors are the same size, I know that they're going to drop evenly across each particular resistor. So since there's 3 resistors, they're evenly going to split the 6 volt drop. So here we're going to drop 2 volts, here we're going to drop 2 volts, and here we're going to drop 2 volts. So each resistor gets a different section of the voltage, like how in parallel they each get a different section of the current, but the total drop across the entire circuit is still 6 volts, and that's what Kirchhoff's voltage law cares about. So total voltage drop across the entire circuit holds true for both series and parallel circuits. And it's the same in the hybrid combo circuits as well. I almost instinctively asked if anyone had any questions, just out of habit. And it's very strange adapting to this new setup, but we'll make it work. We will make it work. Slide number 7. 7 and 8 are just going to be quick review of the different circuit types. We have series circuits. Everything is wired in a series. Everything adds up linearly. The resistance adds up linearly. The things to know about resistor series circuits is, and I will reiterate this on the board as I say it. So, in series, R equals the sum of all the R's in the circuit. Everything gets the same current and different voltage. Well, different voltage drop, I should say. Everything gets its own unique voltage drop, and the same current travels through everything. Slide number 8 is just review of what makes up a parallel circuit. So, just to put it on the corner of the board for sample questions in a minute, parallel circuits. You find the total resistance in a parallel circuit by taking the inverse of the sum of the inverses. Everything in a parallel circuit has the same voltage drop and a different current. So I put those up on the corner to reiterate them, and they'll be useful in a second where we do some quick review problems. Now, Those problems are on slide number 9. Go ahead and look at slide number 9. On slide 9, there are two completed circuits. They both have the same battery and the same resistors, just one of them is in series and one of them is in parallel. I'm going to put those up on the board now. And what we're going to do with each of these is we're just going to analyze them both separately and find total resistance for each circuit, the total current in each circuit, the voltage drop across each resistor, the current through each resistor, and the power used by each resistor. We'll do that one circuit at a time. Just drawing up real quick. So we have 10 ohms and 2 ohms. Then in the parallel circuit, still a 9-volt battery. So this one's 10 ohms, this is 2 ohms. Okay, so we'll just compare and contrast and find each of these things for each of our resistors as we step through. So, total resistance for each circuit. Total resistance for each circuit. So, total resistance in a series circuit, you simply add everything together. So 10 plus 2 gives you a total resistance of 12 ohms. In series, resistance always goes up. Parallel takes a little bit longer. So 1 over R equals 1 over 2 plus 1 over 12. That means that our parallel is going to be 1 over 2 plus 1 over 12. So 1 over 2 plus 1 over 12 is going to give you 0.5833 repeating. But you then have to invert your answer. So the final resistance of the whole circuit is 1.71 ohms. In parallel, their combined resistance is always smaller than the smallest resistor. Notice between 10 and 2, our smallest was 2, and now our resistance has dropped even lower. Series resistance goes up, parallel resistance goes down. So for each circuit, we've now found the total resistance within each. Next question, the total current in each. I'm going to start putting formulas back up on the board now. So, V equals IR. This statement is called Ohm's law. We know the total voltage across each circuit. We know the total resistance of each circuit, so we can find the total current in each circuit. So, total voltage equals total current times total resistance. Total voltage drop is 9. Solving for current, our total resistance is 12. So, our total current for this entire circuit, this entire series circuit, is going to be 12 divided by 9, which is 0.75 amps. Carry my calculator around. Now, in parallel, total voltage equals total current times total resistance. 9 equals total current times 1.71. So our total current is 9 divided by 1.71, which is 5.26 amps, which is a lot. So that's the total current in parallel, total current in series. Next question. Voltage drop across each resistor. Voltage drop across each resistor. Well, in a I'm going to do these in order of simplicity. In parallel, every resistor gets the same voltage drop. Every resistor gets the same voltage drop in parallel. So, grab a different colored marker real quick. Let's make voltage red. So, here, everything's voltage drop. Voltage drop across resistor 1 is the same as voltage drop across resistor 2. They're both going to drop 9 volts. We have 9 volts coming out of the battery. It's going to pass through both resistors and get used up at the same time in both paths. And then you have 0 volts going back into the battery. So both resistors here have a drop across them of 9 volts. That's a little bit different over here. It's a little different over here because here the voltage is going to drop across the first one, then it's going to drop across the second one, then come back into the battery. So this zone is 9 volts, this zone is 0 volts, but there's a mystery zone between the two. So we have to do a little more math to find the voltage drop for every single one here. Now, to find the voltage drop for a single resistor, you need to use V equals IR for a single resistor. Now, in what we did earlier is V equals IR for the entire circuit. V equals IR for the entire circuit. We now need to look at each element one at a time. So, to find the voltage drop across, how much of the 9 is going to drop across this 10 ohm resistor, we need to do V equals IR for the 10 ohm resistor. So, V equals IR for our 10 ohm resistor. So we're solving for V. I should have wrote, sorry, all my voltages I need to put in the same color. So, V equals IR, so I'm going to put voltage through the 10 ohm, V equals IR, voltage through the 10 ohm equals, we need to know the current through the 10 ohm resistor, current through the 10 ohm resistor in series. Now, interesting shortcut with the series circuit. Every element in series gets the same current. There's only one place for the 0.75 amps of current to go. That means both resistors in this series circuit got 0.75 amps of current. So we're going to skip ahead a little bit now. The current through resistor 1 is the same as the current through resistor 2, and that is 0.75 amps. So in series, we can assume that every element gets the same amount of current. We can use that to find our voltage drops. So the voltage drop across the 10 ohm resistor should be equal to the current through the 10 ohm resistor, which is 0.75, times the resistance of the 10 ohm resistor, that's 10, and that should give us a resistance drop across that resistor of 7.5 volts. 7.5 volts. We can do the same thing for the 2 ohm resistor. So V through the 2 ohm, the voltage drop across the 2 ohm resistor equals IR. It's going to be current through the 2 ohm, current resistance of the 2 ohm. I should write in 10 and 10 here. So voltage drop across that one equals the current through the 2 ohm resistor is also 0.75 amps. Also 0.75 amps. And its resistance is 2. So the voltage drop across resistor 2 is 1.5 volts. Now notice, the total voltage drop, 7.5 plus 1.5, is equal to 9. We dropped a total of 9 across both of them. So if we dropped by 7.5 from 9, that means the amount of potential here is 1.5 volts. We dropped by 7. Therefore, dropping from here to here would be the rest of the 1.5. So the sum of these two voltage drops is the voltage drop of the entire circuit in series. Now, we can take what we just used and apply it to our parallel circuit. So, we know the voltage drop across each resistor. We don't know the current through each resistor, because in parallel, the current is going to split and a different amount of it is going to go down each pathway. So we need to do V equals IR for each individual resistor. We know each one's resistance though, and we do know the voltage drop across them. So we can figure out the current using V equals IR. So, voltage through, we know the voltage across the 10 ohm. So, 9 volts across the 10 ohm resistor. I'm going to find the current through the 10 ohm times the resistance of the 10 ohm, which is 10. So the amount of current passing through the 10 ohm resistor is going to be 0.9 amps. Meanwhile, there's a 9 volt drop across the 2 ohm resistor. So this current to the 2 ohm resistor times its resistance of 2 should be equal to its 9 volt voltage drop. So what is 9 divided by 2? That's going to be 4.5. Amps, 4.5 amps. So, 0.9 amps branched off to go here. 4.5 amps branched off to go here. After they split, they're going to come back together to go back to the battery. After they come back together, 4.5 plus 0.9 is 5.4. It's about what we had before. I'm just going to chalk that difference up to rounding error. So, Kirchhoff's current law holds true here. The amount of current that exits the battery did split, but it came back together and went back into the battery. So, for each resistor, we now know the voltage drop across it and the current through it. The last question is, what is the power used up by each resistor, which we can now calculate. We have all the information we need to find power. So, I'm running out of board space here. I am going to erase the blue and the green. So we already found the total resistance. We found the total current for each. We're going to erase these to make room for power. Now, we have many different formulas for power. Going to put them all up for us to look at real quick. Electrical power equals I times V. It can also be equal to V squared over R. It can also be equal to I squared times R. So for each resistor, we just have to pick one of these three things to find the power running through it. So, for the series circuit, everything gets the same amount of current through its different resistors. So, I'm going to say power through the 10 ohm is going to be equal to the current through the 10 ohm, which is 0.75, squared. So I should specify. I'm using P equals I squared R. P equals I squared R to find the power used up by each resistor in this particular circuit. So, for the 10 ohm, power of the 10 ohm equals current through the 10 ohm times resistance of the 10 ohm. Current through the 10 ohm is 0.75 squared. The resistance of the 10 ohm is 10. Meanwhile, current through the 2 ohm is still 0.75. Multiply that by the 2 ohm resistance of that particular resistor, and that will tell us the power used up by each. So, 0.75 squared times 10 is 5.625. The unit of power is watts. And then 2 times 0.75 squared gives us 1.125 watts. So that's the power used up by each one in series. In parallel, we know everything has the same voltage drop across their resistors. So I'm going to use now P equals V squared over R for this one, just because I know for certain the resistors and the voltages. So P10 equals V squared over R. So voltage drop across everything here is going to be 9. So 9 squared over the 10 ohms resistance. I'm going to write around this little blosh right here on my board So 9 squared divided by 10. That's going to be 8.1 watts used up by the 10 ohm resistor in this circuit. Now, through the 2 ohm, V squared over R. So it's still a 9 volt drop, because in parallel everything is the same voltage drop, divided by its 2 ohm resistance. So 9 squared divided by 2, that resistor is going to use up 40.5 watts. 40.5 watts. So that's the power that each resistor used up in the circuit. If you wanted to know the power used by the circuit as a whole, the total circuit power used up, you just add these together. So this particular circuit used up both of these added together in terms of the power. So that would be 6.75 watts if you add these together. This circuit, meanwhile, used this circuit used 48.6 watts of power. So these light bulbs would probably be brighter, but they would also run the battery out faster. They are pulling more power out of the battery per unit time. So these would get you brighter lights, but the battery would die faster. Something to be aware of. Benefit to a series circuit. That's one benefit to a series circuit. The battery does last longer. So that is our review for RC circuits and using your power formulas. So slide 10 is just review questions. Look over these, make sure you understand how to do them. If we move on to slide 11, oh no. What? Okay, sorry, my slideshow glitched a little bit. Slide 11 has a bunch of images, rapid fire. Skip to slide 12. Slides 12 through 15 are those pictures, but with further elaboration. So skip slide 11. Instead, go straight to slide 12. So, slide number 12. We're now moving on to RC circuits. These are circuits that have a resistor and a capacitor in them, at least one of each. Now, the function of a capacitor is to hold electric charge. So, I'm going to erase the board and draw up an RC circuit so that I can point and draw on it. Hope you're all having decent days. Hope you're all staying healthy. Make good choices. Again, this is not ideal for anybody, but we're all just going to work together, try to stop this bug before anyone who is susceptible to it suffers. We're all going to be fine. We will all make it. Alright, so I'm going to draw the RC circuit in the notes. So we have battery, and this is actually the positive side of the battery. We have the capacitor, and we have the resistor, and that is our RC circuit. So, the purpose of a capacitor is to hold an electric charge. When you build this circuit and allow current to flow through it, electrons are going to flow through the circuit. As the electrons travel through the capacitor is going to start accumulating those electrons. It's kind of like a little battery. It's going to store the electrons within them. So, as the current flows through it, some of the electrons stay behind inside of the capacitor. Now, this is what happened when we did our capacity lab before. And when the capacitor has all of those electrons, they stay there for a while. Right now, when the circuit is wired and current is flowing, this is the charging phase, because you are using the circuit to charge, build up charge within the capacitor. And this takes a certain amount of time based on what the circuit configuration is. Factors that affect this include the voltage of the circuit, the capacitance of the capacitor in question, and the resistance of the circuit in question. These all affect how long it takes the capacitor to charge up to its maximum value. They also affect what the maximum charge on the capacitor is. A certain capacitor of a certain capacitance, if you'll remember, so this is a capacitor. The capacitance of a capacitor, the actual measure of how many electrons it can hold, C, is measured in units of farads. So, this is our capacitor. Its capacitance is measured in farads. This is our resistor. That's measured in ohms. Voltage is measured in volts. So, depending on the capacitance of the capacitor and the voltage of the circuit, or rather the voltage drop across the capacitor, that determines what the maximum charge that the capacitor can hold is. The capacitor can only hold so many electrons within it, because what it's going to be physically holding on to is the electrons. That's what's moving through the circuit. That's what's being stored in the capacitor. So there's a bunch of electrons inside and between these two plates. They're just staying there. They've been accumulated. They're hanging out. And the maximum amount of charge that a single capacitor can hold, so Q max, is equal to the capacitance of the capacitor in question times the voltage difference across it. So, if this was a 1 farad capacitor and there was a 1 volt voltage drop across this particular capacitor, then it would be able to hold 1 coulomb of charge. So 1 farad times 1 volt is 1 coulomb of charge. And so once you connect the circuit, the electrons start flowing, and over time, an amount of electrons is going to accumulate inside of the capacitor equal to 1 coulomb worth of charge. But how long that takes depends on the resistor, because the resistance of the circuit determines how fast the current moves through the circuit. And the speed of the current affects how many electrons move through the capacitor every single second, and that affects how long it takes the capacitor to accumulate those electrons. So the main features of an RC circuit are: the capacitor will begin to charge up to a certain maximum charge level, and that takes a certain amount of time, so T equals time, based on the resistance of the circuit. So that's slide number 12. Moving on to slide number 13. There's a funny looking scary graph right there. Don't worry. I'll explain the graph, and I'll explain what the paragraph beneath it means. I'm going to draw the graph in the corner of the board real quick, just so that I can point to it. So you should be seeing right now a curve that is exponentially leveling off. So this curve starts off increasing, and then it starts increasing less and less and less until it levels out. And this particular graph is a charge versus time graph. Sorry, I'm using lowercase t for charge. Sorry. I'm using lowercase t for time. Excuse me. So, what this graph represents is the charge accumulated by the capacitor as a function of time. All capacitors, when you first turn the circuit on, they initially start charging up really quickly. And so every single second or unit of time that is passing, initially you're building up a lot of charge in a short amount of time. Within a second, you're charged up to like 50%. Within 2 seconds, you're at like 60%. But then the increases become less and less and less as you start approaching and leveling off at Q max. So that is the maximum charge of the capacitor.
It can't hold any more than Qmax. It's going to approach Qmax, and then it's going to start leveling off slowly. It's not going to skyrocket straight to Qmax and then stop. It's going to level off slowly. And if you've taken a few math classes, this may look familiar to you. That means, technically speaking, the capacitor might never actually become 100% charged because this line is just approximating that line. This curve is just getting approximately closer to Qmax. But for the sake of this particular class, if it is close enough to the line, we can assume the capacitor is fully charged. So looking here, and this amount of time, the capacitor has become fully charged. So, the charge level of a given capacitor, the charge level, that's not my good red marker. Where's my, this one has more ink in it. This is my good red marker. Q charge equals, so this is how much charge the capacitor actually has. So this is this line of the graph. This tells us Q charge is how much charge does the capacitor have right now as I'm looking at it. The way to figure out how much charge is in a capacitor depends on what is the capacitor's Qmax. Qmax times 1 minus natural, no wait, this is like the E related to the natural logarithm. This is the inverse of the natural log E. This is not the E in your calculator that means times 10 to the, this is the E raised to the something power, and this is the inverse of natural log E. I'll remind everyone what button on your calculator you need to press. E raised to the power of minus t, this is time, divided by, I'm just going to write RC up here. So this formula looked kind of funny. I probably haven't done a very good job explaining it yet. What this formula represents is the charge in a capacitor a certain amount of time after you turn the circuit on. So T is time. T is time. When you first turn on your circuit, time equals 0. So this is 0 on our graph. We are at 0 charge and 0 time. At that time, no charge, no time has passed. As time starts ticking forwards, as this number stops being 0 and it starts getting bigger, the capacitor starts accumulating charge. So every single moment of time after you begin, as t gets bigger, the charge on the capacitor gets bigger and bigger and bigger. And after a certain amount of time has passed, your Q charge will be basically equal to your Q max. So the goal of the capacitor is after a certain amount of time passes, so this is time, it will charge up to its maximum charge. And that just takes a certain amount of time. That's all it means. Now, in your notes, the formula given there is time divided by tau. That's the Greek letter tau. Tau is just a constant equal to RC. So if this is the circuit we are looking at, you multiply this resistance times this capacitance, that value is tau, and it just lives right here. So tau is RC, it goes here. Anywhere you see tau, it's just R times C. And Q max, as written up here, is capacitance times the voltage of the circuit. I need water. I've been talking for too long.
realizing probably going to have to go over a lot of this again during the study sessions. That's fine. This video is just a teaser, not a teaser, just to get you started on everything on Monday so that you can come prepared with questions the rest of the week. So, what this formula represents is the point of a capacitor is to build up charge. The point of a capacitor is to build up an amount of charge. Eventually, it's going to charge up to charge max, but that only happens a certain amount of time later. It takes time to build up to Qmax. And that amount of time is what you see on this graph here. So the point where you are fully charged, you look down, that's the time you need in order to fully charge. And that's what the graph on this particular slide represents. So, just to read the notes out loud, a capacitor in an RC circuit accumulates a charge Qmax based on the max charge it can hold, how much time is passed, and tau. Tau just represents R times C. And it really bothers me. I can't ask if you guys have any questions. If y'all need a break, feel free to pause this. I've been going for probably like an hour at this point. I need a break. Slide 14 elaborates on what tau represents. So, how you find tau, the actual value of tau, is R times C. But it does mean something. We've noticed that tau, the number for tau, is the number of seconds it takes. Whoops. For the capacitor to reach 63.2% of its maximum charge. So if you know tau, you know that you know what T will at what time Q charge will be 63.2% of Qmax. And subsequently, if you scroll to slide 15, we've also realized that if you multiply tau by 4, then you get approximately the amount of time you need to completely charge the capacitor. It's not exact. 4 times tau is not going to be exactly the time required to charge up to Qmax because, again, technically speaking, as the graph goes on and it's leveling off, it never really reaches the line. But we've noticed that 4 times tau is like 99.9% charged. That's as close as you're realistically going to get. So if you know tau, you already know 2 very important times. You know how long it takes you to charge up to 63%. You know about how long it'll take you to charge up to full. And the reason why the gain levels off slowly over time is because when the capacitor reaches its maximum charge, it stops letting current through it. When it is fully charged, it doesn't let current move through itself. Once it's full, it's just kind of jammed up. It doesn't do anything else. So in this particular circuit, the current is going to flow, the capacitor is going to fill up, but after a while, once it's full, it's not going to let any current through anymore, and the circuit's just going to stop. And as the capacitor gets more full, the current starts slowing down until when you're at full and the current just stops completely. So the capacitor just stops letting current through over time. And because there's no current coming into, because the rate of current is slowing down, the rate at which it fills up slows down until, again, at the end, your barrel, like the rate of increase is incredibly small, but at that point, you're basically already filled anyway. So, something to be aware of. I'm going to write it in the corner of the board. Please write it in your notes. As time passes, and the capacitor fills,
it stops letting current through it. It stops letting current through itself. So if this was the entire circuit and we left it turned on, after the number of seconds required to charge up this capacitor, once it's charged, the circuit just stops. It just turns off. It's still connected. Current could still flow. It's getting jammed up at the capacitor because once it's full, nothing else can get through it. So, that's slide 15. That is the basics of an RC circuit. The very basics. Take a minute to drink real quick. How long have I been going?
1 hour exactly. By golly. Okay. We got one sample problem to get. Well, it's a multi-part. Oh, sorry. I jumped the gun. Slide 16 is a little extra information. Ah, crud. So slide 16 is extra information. When the circuit is allowed to flow, you will eventually charge up until you hit your maximum charge. When you disconnect the circuit, this begins a process known as discharging. Once you disconnect the circuit, now the capacitor is able to continue to basically empty itself. Now that current is no longer being added into it, it's just going to dump all of its charge into the rest of the circuit. So, once you break the circuit, the charge level of the capacitor is going to begin dropping. It's just going to let out all of its charge slowly over time. It's just going to start leaking out. And that's going to take a certain amount of time. It's going to take a certain amount of time depending on, again, the resistance of the circuit, the capacitance of the capacitor, and how much charge was in the capacitor when you emptied it. Because you can unhook it before it's full. You can unhook it before it is full, and then technically it won't... Okay, so I'm going to put an extra formula here on the board. The formula from before is about charging the capacitor up. That is the charging period. The formula on slide 16 is for discharging a capacitor. So here it's charging up, here we are discharging down. The formula is slightly different to before. Instead of the maximum charge of the capacitor, we have Q naught. This represents the charge of the capacitor when you began discharging. Because technically speaking, you don't have to be at Q max to start discharging it. You can be watching the circuit fill up, you can be watching the capacitor fill up, but if you unhook it here, like at this time, instead of this time, you weren't at Q max. So the charge in the capacitor is not equal to Q max. So instead of Q max in the formula, we just care about how much charge was in the capacitor when it began discharging. And that is then multiplied by E, natural exponent, raised to the negative time over tau. That's supposed to be tau. That's the same tau as before, and this represents the time it has been discharging. The time it has been discharging. So here, this is the time it has been charging. Now it's the time it has been discharging. But you still find tau the same way. You still find tau the exact same way.
There's a different graph on slide 16 that you are the slide you are currently on. I'm going to put that one up here just to compare and contrast. So this graph represents the discharging process. You start at a certain original Q naught, and then over time, you lose that charge. And like how originally you charge up really fast and then level off, here you discharge really fast and then level off. Next slide, slide 17. Tau still represents something here. So before, tau was how long does it take to charge up to 63.2%. But here, it also represents the amount of time it takes to decrease charge by 63.2%, which you could also write as the amount of time it takes to drop to 36.8%. It's still the same number. It still represents a change by the same amount of the total. And subsequently, 4 times tau is still approximately the amount of time that you need to completely discharge still. So having tau is still very beneficial. Okay, so moving on from 17 to slide 18, we now have an RC circuit sample problem. So this is a circuit that contains multiple resistors and a single capacitor, so this is an RC circuit. This represents a little switch here. You can close it to turn everything on and open it to turn everything off. So just be aware of what this symbol is when it shows up in other diagrams. So we have our battery here. Current's going to exit the battery, go through the switch. It's going to hit this junction where some of it can travel through the capacitor, through this resistor, and then out of the junction. Some of it could also go down this pathway instead through a 2 ohm resistor. They're going to meet back up here. Then the current has to go through the 1 ohm before it gets back to the battery. So this is a hybrid. It is a hybrid circuit and an RC circuit, both together at once. The things that we need to find here are tau, Qmax, the current through everything as soon as you first turn the circuit on, and the current through everything after the capacitor has fully charged, because they are going to be slightly different. Very different, actually. So, the trick to RC circuits is the capacitor only really cares about what's on its branch. So, this capacitor, this 1 farad capacitor, is on a branch with this 1 ohm resistor. Therefore, it's also only outside of this whole thing in series with a 1 ohm resistor. So, I erased it. The formula for tau is R times C. So, resistance of 1 times the capacitance of 1. Our tau is 1 second. The unit for tau is seconds, time, because it is a measure of the time it takes to charge up to 63.2% of your Qmax. Next, Qmax itself. We need to calculate Qmax. The formula for Qmax is CV, the capacitance of the capacitor, times the voltage drop. Now, the thing is, when that particular capacitor is at Qmax, once this thing is fully charged, and to represent fully charged, I'm just going to put some red squiggly lines in it. Once it is fully charged, it doesn't let any more current through. It's juiced up, it's happy, nothing has a very easy time passing through it from that point on. And so basically this whole branch of the circuit is just functionally disconnected. Which means our circuit has essentially become just a series circuit with this 1 ohm and this 1 ohm and this 2 ohm resistor. Now, there is still a voltage drop across this particular branch. It's just the only way to find it is by ignoring these for the time being. So what we need to do is figure out the voltage drop across the 2 ohm resistor, because that is the drop from this zone to this zone, which would be the drop across this even when it's fully charged. So in order to do CV, we need to find the voltage drop across the 2 ohm resistor when this branch is functionally disconnected. So in order to do that, to find that particular voltage drop, we're going to have to do V equals IR for the total circuit after everything has filled up. So I'm going to put in final for all of these. We've got voltage final, total circuit voltage final, total current final, total resistance final. The circuit still has a voltage of 6. We want the current in the circuit final and the resistance in the circuit final. This has basically just become a series circuit now. If this branch is gone, current will travel through the 2 ohm, through the 1 ohm, and back to the battery. They're in series now, so the resistance is just 3. That means the total current is going to be 2 amps. That is the total current passing through this part of the circuit once this branch is filled up and no more current squeezes through it. So, for this particular resistor now, for that particular resistor, I'm going to do V equals IR. This is after the capacitor has filled up. So, we're solving for its voltage drop. If you squeeze 2 amps of current through its 2 ohms of resistance, that means its voltage drop is going to be 4 volts. Once this has filled up, and this is basically no longer a part of the circuit, you're going to drop 4 volts across the 2 ohm resistor, and then the remaining 2 volts across the 1 ohm resistor. And because the resistances are, this one's twice as big as this one, it makes sense it would have twice as big of a voltage drop. So, the voltage drop across this resistor would be 4 volts. Therefore, the voltage drop from here to here, even though the capacitor is filled up, would also be 4 volts. So, that's the voltage that we put into our formula here, because that would be the voltage drop once it's filled, once it is filled. So, lost my train of thought, sorry. So, we still have a capacitance of 1 times 4 volts voltage drop across it. That means our Qmax is going to be 4 coulombs. It's measured in coulombs because it is the maximum charge. Sorry, I looked at my camera light was off for a second there, and I got really paranoid. All right, we are still recording. We are still live. Very good. So, we've now figured out tau and Qmax. Now we need to figure out the current through each part of this circuit. In order to find the current through any one element, we need to figure out what the total current is. In order to find the total current in a circuit, you have to do total V equals IR. And this is all, right now we're just looking at before the capacitor fills up. So, total voltage initial equals total current initial times total resistance initial. Total voltage is 6. We're looking for the total current, and we need to find the total resistance in the circuit before the capacitor fills up. So, before the capacitor filled up, these 2 resistors are in parallel with one another, and they together are in series with this one. So this is a hybrid circuit. First thing we need to do is parallel these 2 things together. So that's going to be 1 over R equals 1 over 1 plus 1 over 2. That R is going to become 0.67 ohms. That 0.67 is in series with this 1. So our total R initial before the capacitor fills up is 1.67 ohms. So we can bring that over here. Total voltage across the whole circuit is 6. We're solving for the total current before the capacitor fills up. Total resistance before it fills up is 1.67. If you solve for the total current in the whole thing, that tells you, and that is going to be, 3.6 amps. That is the total current through the entire circuit before the capacitor has begun charging. So, looking at each of these resistors, I'm going to write the answers in order of this one, and this one. This element is in series with everything else. The current splits here, comes back together, and then all of it has to go through here. So this particular resistor is getting all of this 3.6 amps. So the first resistor gets 3.6 amps. Next, the other two. They're in parallel, meaning when that 3.6 amps hits this junction, it's gonna split. It's gonna split. Once it splits, some of it goes here, some of it goes here. So these two currents have to add back up to this. And this particular pathway has twice as much resistance as this one. That doesn't mean the current gets split in half. It would only get split in half if the two were equal, and then the current, 50% would go this way and 50% would go this way. Instead, we're going to divide it into 3, and 2 of those thirds are going to go here, 1 of those thirds is going to go here. So, if we split this, the current through one of them is going to be 2.4 amps. The current through the other one is going to be 1.2 amps. So, the 1 ohm pathway has less resistance. That means more current is going to travel through it. And because it has half as much resistance as this path, it's going to have twice as much of that current. So this current is twice the other one. This one is half as big as this one. But notice, they both still add back up to 3.6. They have to add back up to 3.6 because that's what came into their junction. That's what has to come back out of their junction. So this one right here is going to get 2.4. This one right here is going to get 1.2. Next, what happens once the capacitor is fully charged? Once it is fully charged, it kind of just disconnects this pathway. Current can't travel through it anymore. That means that this particular resistor gets no current. It's been cut off. So the answer for that particular resistor is just going to be 0 amps. Meanwhile, our analysis from earlier tells us that there's 2 amps of current flowing through the circuit once this branch is disconnected and the capacitor is full. That 2 amps has to go through this resistor and this resistor, so they both have a current of 2 amps. That then is the current through each resistor in both stages, when the circuit is first turned on versus once the capacitor is full. And that's everything that's on this slide. If you move forward to slide 19, we ask just a couple of more questions. Utilizing the knowledge that tau is 1 second and Qmax is 4 coulombs, what will be the charge on this capacitor at half a second, 1 second, and 2 seconds? To work that, we are going to turn to this formula. This formula represents the charge as you are charging up the circuit as a function of time. So, the way that you're going to use this is, what we're solving for here is Q charge. We want to know what the charge is at a specific moment of time. So, let's say we want Q charge at half a second. We want to know what the charge in the capacitor will be if we leave it plugged into this circuit for half a second. So, it's going to be equal to Q max, which is 4, times, open parentheses, 1 minus E. This E is the one that is inverse of natural logarithm. I'm going to show you where to find that on your calculator in a second. Raised to the, that's E raised to the negative T negative times time. So the time we are looking at here, the problem says, what is the charge at 0.5 seconds? So our time is 0.5, and our tau is 1. Tau is a constant. We found it earlier. Tau is 1. Now, the buttons that you want to press on your calculator to actually work this. The E in question here, this is not E as in times 10 to the. That's a different E on your calculator. This E is the natural log E. So if you look on your calculator, you should have a natural log button, that's ln, and up above that is E raised to the something power. That's the E that we want. So hit second, hit that button, and you'll get a lowercase e raised to the something power. We want that e raised to the negative 0.5 over 1 power. So negative 0.5 divided by 1. The divided by 1 is not really going to do anything, but I'm including it for completion. If you press that, we get 0.606. Now, that's just this piece. That's just this tiny piece. You still have to subtract that from 1, and you still have to multiply that by 4. So, what I'm going to, real quick, I'm going to modify what I have in my calculator here to show you what you should have to get the full answer. So that's 4 times, open parentheses, 1 minus e raised to the negative 0.5 divided by 1 power. Press enter, and we get 1.57 seconds. Sorry, 1.57 coulombs. My apologies. So, that's our answer. After half a second, we have charged up 1.57 coulombs. Great job. Now, to find our others, to find the charge after 1 second, you do the exact same thing, you just put in 1 second instead. So, I'll show you my calculator. I've copied what I did before, but I'm going to change the 0.5 to be just a 1. So now it's 4 times, open parentheses, 1 minus e raised to the negative 1 over 1. Press enter, and we're going to get an answer of 2.53 coulombs. And if we work it again for 2 seconds, if you plug a 2 in instead, you get 3.46 coulombs. So these are our charge levels at different moments of time. You have half a second, 1 second, and 2 seconds. Notice, doubling the time is not doubling the charge. Every time we double the time, we're not doubling the charge. That's because our increase is exponentially decreasing over time. We are leveling off. We have a big jump, and then we slow down. Now, last question on the slide. How long does the circuit need to run for the capacitor to be fully charged? A capacitor tends to fully charge after a number of seconds equal to about 4 times tau. So 4 times 1 second is 4 seconds. That is approximately when we will reach our maximum charge. To prove that that works, you would just plug 4 seconds into your calculator. So Q at 4 seconds equals Q max, which is also 4, coincidentally, times 1 minus e raised to the negative 4 over 1. If you work that and get your correct answer, you should get 3.93 coulombs, which is really, really, really dang close to 4 coulombs. So it did charge in approximately 4 times tau seconds. Again, it'll never be perfect because we're doing that math thing where we're leveling off slowly and we never actually reach the line. But this is as close as we care about in this class right now. So 4 times tau seconds fully charged up the capacitor. And it would take 4 times tau seconds to completely discharge the capacitor as well. When you come over here and you disconnect the circuit, this capacitor is going to start releasing all of its electrons out of itself, and in order to fully empty itself, it would also take this many seconds again to go from Qmax down to 0. So, that is all the preliminary information from Chapter 18. We're going to have our study sessions over the week. Please come to those. I will send out a Google Meet link for all of them. Again, the goal is for you to be able to come as you are available. Try to attend at least 2 to 3 hours worth of the study sessions a week. This is my first time doing anything like this. This is a weird, crazy thing for all of us. And so I want to make sure that we all have a chance to succeed here. You guys deserve that. So if how I'm doing this now, if this format doesn't work, I will change it. I will figure out how to best run this course for you guys. We're going to make this work. Come prepared to the study sessions with your questions. And y'all are going to pass physics. I know it. Let me know if you have any pressing questions via email, and I'll talk to you all soon. Have a great day, guys.